So we've looked at nucleophiles, we've looked at electrophiles, we've looked at leaving groups. Missing one last thing. Missing solvent. And you go, well, what is solvent? Solvent, think about solvent. Solvent is, formally, it's the substrate in which the chemical reaction proceeds. But think about it more like the dance floor is really what this comes down to, okay? So for the chemical reaction to proceed, you need the molecules to bump into each other. And so solvent really serves kind of as the dance floor. Now the question is, do you want your dance floor sticky, or do you want to be able to move around on it? And there's a big difference between the two of them. And we're going to look at what that difference is here in a second. So let's look at our hypothetical reaction. This is a perfect example of an SN2 reaction, and for a couple reasons here. Let's just analyze it really quickly. First of all, our nucleophile or nucleophilic position is this carbon right here. And you'll notice it's very small. It only consists of 2 atoms. And so what do we say about reaction rates for SN2 reactions with very, very small nucleophiles? Very fast, very, very fast. All right, let's look at the leaving group. BR. Is BR a good leaving group? Yes, absolutely it is. This is a great, great leaving group. All right, so that's good. And you'll notice here it is, the electrophilic position is only touching 1 carbon. So this is a primary alkyl halide. So this is like perfect, absolutely perfect. So what happens in this chemical reaction? It's a substitution reaction. So we break the carbon-bromine bond. We form a new carbon-carbon bond. That is, the cyanide comes in and attacks. Leaving group goes away. Now, what happens if I run this reaction in water versus what happens if I run it in this weird-looking chemical called DMSO? We'll talk about what that is here. When you run the reaction in water, the relative rate is 1, meaning the reaction is very, very slow. But when you run it in DMSO, 1500, really fast. Okay, so what's causing this? Why is this actually happening here? So we should probably start by taking a look at the structures for both of these. So here's our water. And if you kind of think about what the structure for water looks like, it's got a general structure that kind of looks something like this. And when we think about the structure of water, we want to remember that water is very, very sticky, right? So we can kind of think about one side of the molecule as being very electron rich, and then we have another side of the molecule as being electron poor. So we would say that this is partially negative. Let's say partially double negative, I'm sorry. And then let's say we've got the hydrogen atoms are going to be partially positive. So this is in essence what polarity is all about. You have a partial negative side on one side, you have a partial positive on the other side. So it's polar. The partial negative side is going to be attracted to things that are positively charged, and the things that are negative or positively charged are going to be attracted to things that are negatively charged. Now, why does this matter? Well, let's think about this. If I have an alkyl halide that's floating around in the reaction mixture, but I have the cyanide, that cyanide is negatively charged. So if you kind of think about what a cyanide looks like, it actually has a whole bunch of electron density around it. Lots and lots and lots of electron density, and the negative is sort of shared over the entire molecule. So what is that actually doing, or how is water interacting with that? Water is actually sticking to that. So we can kind of think about it forming this attraction. Kind of looks something like this. There's lots of water molecules. And by the way, those water molecules are stuck to other water molecules, and those water molecules are stuck to other water molecules, and so on and so forth. And so what you actually have is a cyanide that's really wrapped in a sphere of water around it. Now, think about this here for a second. If I take this cyanide that has localized electron density on the carbon atom, and I put a whole bunch of water around it, it's almost as if you're preventing that negative charge on the carbon from being nucleophilic. In other words, the big boy, big girl term here is you are attenuating the nucleophilicity of that particular nucleophile. So what happens when we start to form hydrogen bonding? Hydrogen bonding, when we start to form hydrogen bonds, hydrogen bonding surrounds the cyanide, surrounds the nucleophile, and prevents it from attacking. So for that matter, we classify water as being polar protic. You see this effect in things that are protic. That is, they have hydrogens in there. They're capable of hydrogen bonding. So we think about water really as being polar protic. So anything that has an OH or an NH in it is capable of doing this. So anytime you see a chemical reaction, an SN2 reaction, where you have a nucleophile, it's electron rich, and you do this reaction in polar protic solvent, you shouldn't expect to see any product form. And that's because that polar protic solvent is going to surround the nucleophile and prevent it from doing what it needs to do. That is to form that new carbon-carbon bond or whatever it is. Okay, how is that different than DMSO? So DMSO is a little bit different in this case. DMSO, you guys have probably heard. Have you heard of DMSO before? Should have. If you haven't, I'm going to prove to you why you should know about this today. It stands for dimethyl sulfoxide. So let's draw out what this looks like. Yep. Dimethyl sulfoxide. DMSO. Where do we buy DMSO? You can buy it. You buy it a tub full at Tractor Supply. It's really cheap. It is not food for chickens, but good guess on this one. It comes in a tub, usually in a gelatinous state, although pure DMSO is a liquid. It's not a gel at all. So why do we actually use DMSO? DMSO is a so it has the nickname liquid needles. And if you have a horse, you use this a lot in horses, but if you have a horse that has a sprain of some sort or some sort of other contusion on it and it's in pain, what you can do is you can take DMSO. You have to wear gloves when you do this, but you can take some DMSO you get from Tractor Supply and you rub it on their muscle. And it's actually not a muscle relaxant, but it's an analgesic. It kind of brings the pain and inflammation down a little bit. Horse feels a little bit better. Kind of like Icy Hot is sort of the way to it, except it has this really interesting property to it. Why is it called liquid needles? So it turns out that if you actually look at the electronic structure for this thing, it's partially negative on the oxygen and the sulfur is partially positive. It is very, very polar, highly polar. And so why that's so important is because if you take a solution of a chemical, poisonous chemical like hydrogen cyanide, for example, and I guess potassium cyanide would be the better example of this, potassium cyanide, and you make a solution of it with DMSO, and then you get that onto your skin, the DMSO has this really interesting property to it where it can actually drag that solute, bring it into your body without actually puncturing your skin. So people have died this way. As a matter of fact, there's been several spy novels that have been written about this. You know, they had to kill the ambassador to whatever country it is in some spy novel, right? So how do we kill him? Oh, we pretend like we're a doctor and we measure his heart. But before we put the lead on the guy's heart, we got to put a little gel on it to make sure we get a good reading of it, right? And so you put the little gel on there, and there you go. The poison's been inserted into the guy, and he dies a day later, right? That's how, like, spy novels right there. But this is DMSO. Now I say that because when I was working in graduate school, there was a woman that I was working with. She was using a lot of DMSO for one project, and then another project she was actually using a lot of potassium cyanide. and she was a little messy. And there's this one meeting I will never forget. We were in my boss's, we were in the lab, I'm sorry, and my boss came in and he was just doing a walkthrough in the lab, and he was just completely blew a gasket over it because he knew she was working at the bench, at the balance, and the bench around the balance is just messy, just crap all over it, liquid and powder and all that kind of stuff. And he hit the roof over this because we had undergraduates working in the lab, and he said, what are you doing here? And she, why are you so mad at me? And he said, you work with potassium cyanide and you work with DMSO. If you combine the two of them and an undergraduate puts their arm accidentally in it, they're going to die. And I just will never forget that moment, like that moment of clarity when that sort of thing happens. So this is kind of an interesting thing about DMSO. You can buy it at Tractor Supply. It comes in little tubs about this big. So you can do it for horses. I think you can even do, you might be able to do it for cows, but I'm not certain. You have to check with a vet on that one. So why is this so important? Well, it's not protic. It doesn't have any OHs. It doesn't have any NHs in it, but it is polar. And so what's special about this is that when you form your transition state, you'll notice this. You have your nucleophile that forms a dative bond with your electrophile, right? And then you have your leaving group like this. We said that in this particular transition state, we were partially negative in these cases. And what do we say about transition states? Energies. Are they high in energy or are they really low in energy? High, 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 high. Big, big, big energies. Really, really, really reactive, unstable intermediates that get formed. They're not intermediates, but they're structures that get formed. So sometimes these transition states are so high in energy, the chemistry doesn't want to go because it's like going up a mountain and then you like run out of gas, right? So how do you make the transition state drop in energy a little bit? Well, if you run SN2 reactions in DMSO, which by the way, this is called polar aprotic solvent. It will, it may surround the nucleophile slightly, but more importantly, it will surround the transition state as it forms, and it will lower the energy of the transition state. And that's good because now your mountain goes from being 4 miles tall down to like a mile tall. So it's a little easier to get over that transition state is the important point. So polar protic solvents, the point here is that they tend to stabilize the transition state in an SN2 reaction.